Hey, I'm Cliff Olson, Doctor of Audiology and founder of Applied Hearing Solutions in Phoenix and Scottsdale, Arizona. And today I want to walk you guys through my 3D medical animation of how humans hear. This is going to be a really interesting journey for you guys. I'm going to provide my commentary throughout and give you guys some fun facts that you may not be aware of about the human auditory system. All right, let's go ahead and get it started. Sound is a vibration of air particles. The pinna, part of the outer ear, captures these vibrations and funnels them into the ear canal. So the pinna is a really interesting part of your ear. Most people think of it as just the thing that you can get pierced, but all of the contours of the ear serve a purpose. So you have this head-related transfer function. Essentially what this means is that your ears, your outer ear, your pinna, allows you to have localization ability. It aids in localization ability. So both vertical localization, where is it in your vertical plane, as well as horizontal localization. Now both of the ears technically work together with full localization capabilities. It's a timing difference between when sound hits one ear versus when it gets the other ear once it wraps around your head. But generally speaking, the actual physical shape of your ear is very important, and it adds a little bit of amplification naturally to sound. It's around 5 decibels or so. But let's see what happens to sound as it enters the ear canal. As the vibrations travel through the ear canal, the canal's natural resonance boosts their intensity and directs them toward the tympanic membrane, commonly referred to as the eardrum. Now that amplification effect of your ear canal is incredible, so we call this your ear resonance. Essentially, it peaks amplification of sound around 2700 hertz. I actually have a diagram here that you can look at. There's a lot of things that are additive to this, but you get up to 17 decibels of additional gain onto a regular sound coming into your ears. Now, this is actually why noise-induced hearing loss is such a problem, because when you go into a noisy place, that ear resonance actually increases the volume of that sound even more, which can cause more damage. I'll get into that later in this video. The eardrum converts the air vibrations into mechanical energy. Now the eardrum is incredibly thin. We're talking 3 layers of skin cells. You have an outer layer, a middle layer, and an inner layer, and they are extremely sensitive to the vibration of sound. Essentially, the eardrum can move less than 1 atom in terms of distance and still pick up that sound and transfer it through the rest of the ear. Of course, it is very easy to damage the eardrum, so just keep the cotton swabs out of your ears, please. Transmitting it to the malleus, the first of 3 tiny bones in the middle ear called ossicles. The malleus passes these vibrations to the incus and then to the stapes. So the malleus bones are the 3 smallest bones in your body, and they actually significantly increase the vibration of this sound. Fun fact here, if you were to not have these 3 middle ear bones, it would drop your hearing by 30 decibels, which is a massive drop. But essentially their job is to concentrate this vibration of sound from the tympanic membrane and direct it into the cochlea through the oval window. But inside the cochlea is where things get really interesting. Together, the ossicles amplify the vibrations before delivering them to the inner ear, specifically through a membrane called the oval window. Beyond the oval window lies the cochlea, a fluid-filled, snail-shaped structure. Inside, 3 fluid-filled chambers surround a structure called the basilar membrane. All right, so one thing that I did not put in this is that you also have a round window that is next to the oval window. So the oval window, of course, is where sound enters into the cochlea through the stapes bone, but the round window is what actually allows for that pressure change to cause a wave of sound. I want you to think of this like if you had a syringe filled with water and you put your finger over the tip of that syringe and you tried to squeeze the syringe, you wouldn't be able to get any of that water out. But as soon as you move your finger out of the way, you can force the water out of that syringe. If you did not have the round window on the cochlea, you would not be able to send this vibration of sound into the cochlea and have it move anything. The 3 chambers inside of the cochlea are really interesting as well. I won't bore you with the technical information on this, but the fun fact here is that your cochlea is kind of like a battery. So you have these 2 fluid-filled chambers, the upper and lower chamber with paralymph fluid, and then you have an endolymph fluid in that middle chamber. It essentially allows for this mechanical transduction of sound to be converted into an electrical impulse. So let's get into what happens when the vibration of sound actually enters into the cochlea. This membrane is tonotopically organized, meaning different areas respond to different frequencies of sound. The base responds to high frequencies up to 20,000 hertz, and the apex responds to low frequencies down to 20 Hz. So technically speaking, when this vibration of sound enters into the cochlea, it's the high frequencies that it hits first. So if a low frequency sound is coming into the cochlea, it has to travel throughout the entire cochlea, through all the high frequency ranges and the mid frequency ranges to get to the low frequencies. There's some really cool animations online that show that when a certain sound comes into the cochlea, you primarily see the basilar membrane vibrate at whatever range it's coded for. I would have done that, but would have added a lot of time to this animation. Which in turn moves the basilar membrane. Sitting atop this membrane is the organ of Corti, which contains two types of sensory cells: 3 rows of outer hair cells, and 1 row of inner hair cells. So this is where all of the magic happens. I mean, I think that hair cells are some of the most interesting pieces of anatomy and physiology that we have inside of our bodies. Of course, there's a very clear distinction between what outer hair cells do and what inner hair cells do. The outer hair cells are responsible for providing additional vibration to favorable sounds, like speech and music, and restricts vibration to unfavorable sounds, like background noise. Outer hair cells, I think, are like the coolest thing on the planet. They essentially have 5% afferent neural connections and 95% efferent neural connections. Basically what I mean by that is that they receive 95% of their information from the brain. Essentially, the brain gets to control what these hair cells are doing, so it can increase access to sound in certain frequency ranges if it wants those sounds, and it can decrease the vibration of sounds in other ranges that it doesn't want. These hair cells are critical for taking softer level sounds and boosting them enough so you can actually perceive them. And on the other hand, they're also responsible for taking these loud sounds in your environment and reducing them so you can hear in places like restaurants. Very fascinating. Once the outer hair cells have enhanced the vibration of sound enough, the inner hair cells are able to receive these vibrations and convert them into neural impulses. So the inner hair cells actually have 95% afferent connections and only 5% efferent connections. So these are primarily the ones that will take the vibration of sound that have been enhanced by the outer hair cells and convert it into a neural impulse. The fun fact here is that you only have around 3,500 inner hair cells in each of your cochlea. I think a lot of people think that you have millions of these, but you don't have millions, and that's also the reason why you don't want these to become damaged, because you only have so many of them and they don't grow back. These neural impulses travel up the auditory nerve and through a series of complex neural pathways to the auditory cortex in both hemispheres of the brain. Now, one thing that I want to point out here is that the ribbon synapses are really important here. So you could essentially have all of the outer and inner hair cells function, but if you have these ribbon synapses that are not actually converting this mechanical movement of the vibration of sound and turning it into an electrical impulse, then it's not going to be able to stimulate the auditory nerve and send that sound up to the brain. A lot of individuals who do not have a measurable hearing loss do have damage to these ribbon synapses, which causes what we call hidden hearing loss. It is the auditory cortex that interprets these neural impulses, which is how we perceive sound. So what's really interesting about human hearing is that it's done effortlessly as long as you don't have a hearing loss. So the auditory cortex basically processes all of these sounds that you're taking in, but if you end up having a hearing loss, your auditory cortex is not fully engaged, so you have to employ other cognitive effort in order to be able to hear. I'll get into that more here in just a second. Most hearing losses occur when the outer hair cells deteriorate due to age, noise exposure, chemical exposure, head trauma, or genetics. As a result, the natural vibrations of sound may not be strong enough to trigger the inner hair cells to generate neural impulses. Hearing aids help by externally amplifying sound at the precise frequency ranges where an individual has hearing loss. This amplified sound combines with natural sound entering the ear canal, which increases the vibration of the tympanic membrane. So you can see the damage that has occurred inside of this 3D model here. So if you don't have all these hair cells, these outer hair cells in this particular case, functioning properly, not only do you lose the audibility of sound, but you also lose the precision of hearing. And like I said, once these hair cells become damaged, they don't come back. Yes, there is research that's gone in to trying to figure out ways to regrow these hair cells or transplant these hair cells back into a cochlea, but as of right now, none of them have been effective, which is exactly why you should be protecting your hearing. And I'm not just talking about protection from noise, I'm also talking about oxidative stress. I'm also talking about chemical exposure. I'm also talking about head trauma here. Whatever you can do to protect these delicate hair cells, you need to do. As a result, the natural vibrations of sound may not be strong enough to trigger the inner hair cells to generate neural impulses. Now in this 3D model right here, the inner hair cells are intact, but you can also have damage to the inner hair cells in addition to your outer hair cells. And there is a difference between the two. So the inner hair cells, if you damage those, that reduces your clarity of speech immensely. So even if you had fully functional outer hair cells to increase the vibration of sound properly, if you don't have any functioning inner hair cells, it won't matter anyway because you can't trigger a signal up the auditory nerve to the brain, and if you can, it's not going to be a very clear one. Hearing aids help by externally amplifying sound at the precise frequency ranges where an individual has hearing loss. This amplified sound combines with natural sound entering the ear canal, which increases the vibration of the tympanic membrane. So this is where things get really complex with hearing aids in particular. So as you can see in this model here, some of the sound is still entering the ear canal naturally. That's because when people have a hearing loss, usually they have some frequency ranges that are better than others, or they only have hearing loss in a few frequencies. And so what the hearing aid is actually doing is it's picking out some of these frequencies, and then the hearing care professional programs the hearing aid to amplify those frequencies. And then it combines everything back inside of the ear canal to intensify the vibration of the eardrum. Now remember, you have all of these other things still in play. You still have ear resonance in play, so you have to take that into account when you're programming a pair of hearing aids, and a lot of other factors that can go into this as well. Of course, if you're watching me on this channel, you're probably familiar with all of those things if you've watched my other videos. This enhanced vibration travels through the ossicles and enters the cochlea. Once the inner hair cells receive these amplified vibrations of sound, so that's the really cool thing about hearing aids here. You can have a bunch of damage for the outer hair cells, but as long as you have functioning inner hair cells, you can restore a heck of a lot of audibility and clarity to sound. But like I said earlier, if you have damage to the outer and inner hair cells, it essentially gets to the point where even hearing aids can't benefit you, and you need to consider the idea of maybe going the cochlear implant route instead, because a cochlear implant will stimulate the auditory nerve directly and bypass all of these damaged inner and outer hair cells. But if you're one of the lucky ones and you have really good inner hair cell function, hearing aids are fantastic for you. Despite missing or damaged outer hair cells, they are once again able to create neural impulses that travel up the auditory nerve to the brain, effectively restoring hearing. And no, hearing aids do not cure hearing loss. When I use that term restore, what I mean is that we're restoring access to sound again, okay? And so you can actually overcome a lot of hearing difficulties with the use of properly fit and programmed hearing aids. But nevertheless, that is essentially how humans hear. Hopefully you enjoyed this little bit of commentary here. I might go in and break out each little section because there's so much more information that I could share with you guys on this particular topic of human hearing. But if you liked the video, do me a huge favor, click that thumbs up button. And if you are not yet subscribed to the channel with notifications turned on, go ahead and do that as well. And I'll see you in the next video.